Now we're going to develop a partial differential equation solver using the parallel programming features we discussed in an earlier section of this JOLT. We'll leverage modern Fortran's object-oriented programming features to define extensible derived types containing distributed data structures. We'll bind a set of operators to these types and implement the operators as side-effect-free procedures that can be executed asynchronously, even in the presence of communication between images. Our context for this presentation is the equation for unsteady heat conduction in a material with a constant thermal diffusivity, alpha. For demonstration purposes, we'll set alpha to 1, and we'll solve the heat equation on a unit interval. The temperature will be fixed at 1 on the left boundary and will vanish on the right boundary. Our initial condition will be 0 everywhere, except on the left, where it will satisfy the left-hand side boundary condition. At steady state, we expect the time derivative of the temperature to vanish, which implies that the Laplacian of the temperature vanishes. In 1D, this yields the linear temperature distribution shown in this graph. We will solve for temperatures at a set of n evenly spaced discrete points. The differential equation for each point holds the temperature steady at the boundaries and evolves the temperature with a second-order accurate central finite difference formula in space. We will advance these points using a two-step predictor-corrector scheme that first takes a substep equivalent to half the full-time step and then uses the resulting temperatures to complete the full-time step. Now let's translate the first substep into code using software abstractions that resemble the Blackboard expressions of our algorithm. To do this, we'll define a derived type named global field, and we'll declare t-half and t to be of that type. We define a constant alpha, and for demonstration purposes, we'll assume a constant time step, dt, small enough to facilitate stable, explicit time integration. Those with a numerical analysis background will probably note that it is more common to use a different class of time integration schemes called implicit schemes for the heat equation, but our choice here provides one example of the truism that algorithms that perform best in parallel are often different from the algorithms that perform best sequentially. Now, because the compiler won't know how to apply operators to operands of a user-defined type, we have to write several operators ourselves. Evaluating this expression from right to left, we will first need to write a Laplacian operator. The result of the Laplacian operator will be passed as the left-hand argument to a user-defined multiplication operator. The result of the multiplication operator will be passed as the right-hand argument to a user-defined addition operator. Finally, the result of the additional operator will be passed as the right-hand side to a user-defined assignment. In many contexts, the ability to write expressions with user-defined operators is referred to as syntactic sugar, which is defined as a style of writing program statements that could equally well be achieved with other syntax. For example, each of these operators could instead be function calls, and the assignment could be a subroutine call. In the case of modern Fortran, however, the syntactic sugar brings with it important semantic requirements. Namely, Fortran requires that the arguments to user-defined operators be declared with the attribute intent in, meaning they cannot be modified inside the function that implements the operator. Recalling that argument modification is a side effect, Fortran is nudging the programmer in the direction of functional programming. If the programmer decides to also eschew all other side effects, Fortran facilitates communicating to the compiler this decision by designating the function as pure. In the context of parallel programming, this has the important consequence of guaranteeing that the entire right-hand side expression evaluation can take place asynchronously, even when there is communication between images inside an operator, as there must be in any non-local calculations, such as the derivative approximations inside the Laplacian operator. By guaranteeing side effect-free execution, we are guaranteeing that no operator modifies state that any other operator might need. Inside the assignment, we must of course modify our left-hand argument so the user-defined assignment is the only point of synchronization in the execution of the line that updates t_half. We'll see in the next video how Fortran facilitates restricting the synchronization so a given image only synchronizes with its two nearest neighbors. This shows a standard graphical way to describe user-defined types, their data, and the operations defined on those types. This standard format is referred to as the Unified Modeling Language, or UML, and this particular UML diagram is referred to as a class diagram. This UML diagram was generated in part by the ForUML tool from the University of Alabama. ForUML automatically parses Fortran and generates class diagrams. A class diagram for a particular type has 3 panels, as shown here for the global_field type. The first panel displays the type name. The second shows the type's data, which are derived type components in Fortran. The third panel shows the procedures that operate on that type, which are called type-bound procedures in Fortran. Preceding each diagram element may be a so-called stereotype, which typically describes how the element is used. From the stereotypes, we can see that the data inside our global field type will be a real coarray named values. The procedures operating on the type will be two procedures that can be referred to by a name that very nearly matches the type name. In most object-oriented languages, these are called constructors. Primarily, constructors perform the steps necessary to initialize data. For reasons I won't describe here, I recommend appending an underscore to the constructor names. Our generic constructor name global_field_ refers to two actual procedures. One is a set procedure that initializes all global field data, and the other is an only_allocate procedure that merely allocates memory for the data without initializing the data. The functions that implement the various operators each take one or two arguments. Each is named in the argument list followed by its type name. Also, any arguments that do not have the intent_in attribute are preceded by their actual intent, which determines whether the argument is input, output, or both. Although not shown in this diagram, the Laplacian and addition operators produce results of type local field. This relates to a Fortran requirement that functions not produce results that are coarrays or have coarray components. As with many choices in Fortran, the reasons relate to encouraging high performance by avoiding unnecessary synchronizations that might otherwise be required. The local field type contains a regular array, so it is a local data structure defined only within a given image. The dashed arrow indicates a dependency. In this case, the global field type depends on the local field type in that each global field operator produces a local field result. When we write the main program in the next video, we will see how the expressions in our time advancement algorithm determine the operators that must be defined on each of these two types.